Hello and welcome to this tutorial on Born Haber cycles. Now in fact this is the first of two tutorials on Born Haber cycles in which I've divided the subject into their application to lattice enthalpies, which is all about the strength of ionic bonds, and looking also at the covalent character present in certain ionic compounds, how that arises. In the second tutorial I'm going to explain the application of Born Haber cycles to the formation of aqueous solutions of ionic compounds. So this is really the chemistry of dissolving, and it's very helpful to keep these two areas separate in your mind. Now, if you've not done so already, I would recommend that you watch my tutorial on Hess's law, because that gives the basis to this. Born Haber cycles are really just complicated enthalpy cycles based on Hess's law. And secondly, a good piece of advice would be to memorise the definitions. There are a lot of key definitions in this field, and if you learn those definitions, they will guide you into writing the correct equations which you need to be able to link them all together to make these complicated cycles. So do memorise the definitions, and I will of course explain those as we go along. So let's start off by looking at the lattice enthalpy, what this actually means. Okay, I'm just going to read to you the definition of the lattice enthalpy as given in the OCR textbook. It says, lattice enthalpy is the enthalpy change that accompanies the formation of 1 mole of an ionic compound from its gaseous ions under standard conditions. Now, as I always say, do check the precise definitions given in your own exam board, your own specification, and make sure that's the version that you learn. But what I want to do is, before we do the calculations, is just think a little bit about what lattice enthalpy means and why it's referring to the formation of the compound from the gaseous ions. First of all, here is a typical ionic compound. This is sodium chloride, and I've got approximately 58 grams there, so that's about 1 mole of sodium chloride, and it occurs as these little crystals, and if you could see inside there, you would see that it consists of a regular lattice structure of alternating chloride and sodium ions. So you've got this giant ionic lattice, and the lattice enthalpy is a measure, an indication of the strength of the ionic bonds in a particular compound. So remember that an ionic bond, by definition, it is the electrostatic force of attraction that occurs between oppositely charged ions. Any particular ion is going to be surrounded by lots of ions of the opposite charge, and there are also going to be repulsive forces. But the lattice enthalpy, it's defined as the enthalpy change that takes place when 1 mole of a substance is formed from the individual ions in the gaseous state. So if you imagine all of these positive and negative ions are over in the gaseous state, when they come together to form this ionic lattice, energy is released. And in the case of sodium chloride, the value is minus 771 kilojoules per mole. Now the values I'm going to give you, you'll find slightly different values in different textbooks. Don't worry about that, it's the differences that we're interested in the pattern, so don't try and memorise these values. Lattice enthalpies, though, they're always negative. Now it's sort of counterintuitive to think of lattice enthalpies as being negative. It can be easier to think in the opposite direction. Here is a lattice of sodium chloride. How much energy do I need to put in to break this apart, to separate these ions? How much energy do I need to put in? That would be called the lattice dissociation enthalpy. We can easily imagine that if I want to get this chloride ion away from these sodium ions, then I have to put energy in, so that's endothermic. And it follows then that when the lattice is formed, when the chloride ion comes in and occupies this position in the lattice, energy is released. Now, again, thinking about, if I say how much energy do I need to break apart this lattice into the individual ions, how far apart do I have to get these ions to say that I've separated them? If I get them just to here, they're still going to be attracted to the lattice. So when we say into the gaseous state, that means that the ions are so far apart that they're essentially not interacting, they're not feeling an attractive force from each other. And so that's why when we state the lattice enthalpy, what we're stating is the energy that's released as heat, the lattice enthalpy, when the ions from the gaseous state, where they're not actually interacting at all, the energy that's released when they come together and form the ionic crystal lattice, the giant ionic lattice. So that's the lattice enthalpy, and I can write the definition of it of the equation for sodium chloride. It's going to be sodium ion in the gaseous state and a chloride ion in the gaseous state come together to form sodium chloride. I say A ion, I mean a mole of sodium ions, a mole of chloride ions to give a mole of sodium chloride in the solid state under standard conditions. And it's an enthalpy change, and I put a little LE there, and it's minus 771 kilojoules per mole. So if I wanted to break that apart, I would have to put in 770 kilojoules per mole. So if I wanted to, all of that salt there, that sodium chloride, if I wanted to turn that into gaseous ions, a mole of sodium ions and a mole of chloride ions in a gas state, I would have to put in plus, it would be plus 771 kilojoules per mole. So now, before we look at the use of enthalpy cycles, the Born Haber cycles, to calculate these, because obviously you cannot obtain these values by doing experiments, you have to use the Hess's law with a Born Haber cycle. I'm just going to talk a little bit about how the size of these lattice enthalpies differ for different compounds. First of all, they're always negative. Lattice enthalpy changes are always negative. Here then is a little diagram, a sodium ion and a chloride ion, and what we're saying is the lattice enthalpy is a reflection of the energy that's released when a mole of these and a mole of these ions come together, so it's exothermic. And we're thinking about what governs this. Well, the factors that control the size of this are the size of the charges. So if I take, for example, magnesium chloride instead, magnesium chloride, if I draw a Mg2+ ion, and I compare that with sodium chloride, so here's a chloride ion. Now, of course, magnesium chloride is MgCl2. Okay, don't forget that, but I'm just talking about the attractive force between the ions. The lattice enthalpy for magnesium chloride is minus 2,500 kilojoules mole to the minus 1. So that's reflecting the fact that you've got a 2+ charge on the magnesium compared with the 1+ charge on the sodium. So the bigger the charge is on the ions, the more strongly or more powerfully they're attracted together. So when they do come together, you get more energy released. And if you want to break them apart, you have to put more energy in. So if you wanted to break apart a magnesium chloride ionic lattice, it would be plus 2,500 kilojoules per mole. We can also compare this with magnesium oxide, where we've got a double charge on the negative ion as well. So if I do magnesium 2+ and I put an O2- ion over here, and so here the value is minus 3933 kilojoules mole to minus 1. I'll just put a little ×2 there to remember that there's 2 chloride ions with each magnesium. And again, we've got 2 doubly charged ions, 2+ and 2-, so they're attracted together more strongly, so you get a bigger enthalpy. So the bigger the lattice enthalpy, the stronger the ionic lattice, the more energy that's released when the oppositely charged ions come together. Now it's not quite that simple, because increasing the charge increases the attraction, but the attraction decreases with the size of the ion. So if you have a larger ions, it means they cannot get quite so close together, and so they cannot attract each other quite so powerfully. It's a little bit like, say you've got a magnet and you want to attract a paperclip. You've got to put the magnet reasonably close to the paperclip to get a strong enough attraction to attract it. If you've got a paperclip at one end of the room and a magnet at the other, then you're not going to attract it. So the closer these ions can get together, the stronger the attraction between them. We're now going to take a look at the lattice enthalpies of the sodium halides, because these illustrate quite nicely the effect of the size of the ions on the strength of the ionic bonding, on the value of the lattice enthalpy. So by choosing the sodium halides, I'm keeping the charges on the two ions constant. It's always a 1 plus for the positive ion and a 1 minus for the negative ion. The sodium ion is obviously the 1 plus ion, but the 1 minus ion is getting larger as we go from the fluoride down to the iodide. Now these numbers are the Ionic Radii in picometers. So 1 picometer equals 10 to the minus 12 meters. And you're probably more familiar with nanometers, where 1 nanometer equals 10 to the minus 9 meters. So for the sodium ion, for example, I've got down that it's 102 picometers. That's the same as 0.102 nanometers. But I've just chosen to give these as picometers because I think it's simpler to look at than having the decimal points there. But there's otherwise no reason for that. We could equally have used nanometers. I do want to emphasise, however, that you must not feel that you've got to memorise these values. Do not memorise these values. In fact, if you look them up in different places, you'll find different values depending on the source. All you'll ever be expected to do in the exams is to explain the trends. For example, you'll be given the data, the numbers, and you've got to explain the trend in the lattice enthalpy or some other phenomenon. So let's see how the radii affect the lattice enthalpies. I'm just going to draw the sodium fluoride a little bit larger. Here's the sodium ion, and we've said that the radius of a sodium ion is 102 picometers, and put next to it the fluoride ion in the lattice, which is just a bit bigger, and the fluoride ion is 133 picometers. So that enables us to estimate the distance between the centres of the two ions in the lattice if they're packed together as spheres, and this would be 235 picometers. So I've just added together the two radii. Now, the closer charges are, the closer opposite charges are together, they're more powerful, the electrostatic force of attraction between them. That's embodied in Coulomb's law, but you don't need to be concerned about that. You can think of it as like a couple of magnets of opposite poles, a north and a south pole. You know they attract each other. The closer you bring them together, the stronger the attraction. Now, it's always like this in the case of ions, because this is a positive nucleus and this is a positive nucleus. So if you brought them too closely together, eventually you get some repulsion. But remember, you've got electron shells as well. So we're just making this assumption that in an ionic lattice the ions are brought together and that we can estimate the distance between their nuclei, between their centres. And so I can write these values in for the halides. So add the two radii together. That one becomes 235, that one becomes 282, and that one becomes 302, and that one becomes 322. So the actual values don't matter, it's the trend that as we go down from the fluoride to the iodide, the ions are not as able to get so close together, so we'd expect the electrostatic force of attraction between them to weaken. And if I look at the lattice enthalpy values, so the lattice enthalpies in kilojoules mole, to the -1, we find that for sodium fluoride it's minus 918. We go to sodium chloride, it's minus 787, and then we go to sodium bromide, it's minus 742, and then for the iodide it's minus 705. Now you will see different values quoted elsewhere, and you'll see me quote different values. I think I've given a different value for this one when I do one of the Born Haber calculations. It just depends on where you get the information. Okay, these are not cast in stone. What's important is the trend, and you see that as the radius of the negative ion increases, in other words, as the distance between the ions gets larger, the lattice enthalpy becomes less negative. So it means less energy is released when the gaseous ions come together to form the solid. To put that another way, in the case of sodium fluoride, the positive and the negative ion can get close together, so more energy is released when they come together. It's more exothermic and more negative value. Compared with sodium iodide, less energy is released because the ions cannot get so closely together. So the ionic bonding in sodium fluoride is stronger than the ionic bonding in sodium iodide. Going in the other direction, if I wanted to break apart a mole of sodium fluoride from the ionic lattice to make the gaseous ions, I would have to put in plus 918 kilojoules per mole. Whereas if I wanted to break apart a mole of sodium iodide, I would have to put less energy in, it would be plus 705, because the attractive forces between the ions is weaker. And we attribute this to the distance between the ions because the charges themselves are still 1 plus and 1 minus. Now, you don't always see such a neat pattern as this. It may well be that the size of the positive ions are different. You may find questions where you've got to consider both the size of the ions, the radii of the ions, and the sizes of the charges, and you've then got to sort of try and rationalise and explain the pattern in the lattice enthalpy values. This is an energy level diagram, or an enthalpy level diagram, in which the higher something is up the page, the higher its enthalpy. So it's a way of representing the lattice enthalpy, which is when you go from the ions in the gaseous state down to the ionic lattice. So of course I repeat this because it's important you remember this and understand it, so I'll say it in different ways each time. But when the ions are in the gas state, they're considered not to be attracting each other, they're not interacting. As they come together, energy is released, so the lattice enthalpy is going to be minus, and the value I'm going to put here is minus 788. And as I said before, the values in different textbooks will vary, so the 771, I got that from a different textbook, but I'm going to put the 778 here, which is from an AQA book, and that's because one of the examples that I'm going to work through comes from one of the AQA textbooks. Okay, now while we've got this diagram, and before I go on, it's a nice way of seeing also how, if we wanted to break apart this lattice and convert sodium chloride to its ions, we would have to put in energy, so 788 kilojoules per mole. So I'll put the units on here, kilojoules mole to the -1. So that would be the lattice dissociation enthalpy, but we're not concerned with that at the moment. Oops. So I'll remove that for the moment because that's the one we're going to be trying to find out. We're going to use the Born Haber cycle that we're constructing to obtain this value, because this is the one that you cannot measure experimentally. So if you've seen my video on Hess's law, you'll understand how we've got to find another route from between these two, and a common step would be to have the elements in their standard states. So if I look at the elements you need to make sodium chloride, a mole of sodium chloride is a mole of sodium which in its standard state is in the solid state. Chlorine comes as Cl2 in the gas state, but to make 1 mole of sodium chloride I need half a mole of chlorine molecules, and you will recognise that this is the enthalpy change of formation. So this is the enthalpy change of formation of sodium chloride, and the value there is minus 441 kilojoules mole to the minus 1. So this one we're looking for, that's its proper symbol, lattice enthalpy, and we don't know what it's going to be. So if you have watched my tutorial on the on Hess's law, you'll know I talked about this is one particular town, this is another town, and if this road's blocked you can take a different route. So the way we can complete this cycle is we can find another route, another connection from the elements in the standard states to the ions in the gaseous state, and the route we would be taking is we would go up there and up there. So to get from sodium in the lattice just to the elements, that would be plus 441 kilojoules per mole. Remember, this time we're going to the elements, we're not going to the gaseous ions. So Born Haber cycle, it's all about finding another route from the ionic lattice to the gaseous ions, and from that you can deduce the lattice enthalpy. Now in the textbooks they give you strings of numbers with alternating plus or minus signs and brackets, and it's very confusing. I'm going to show you a very simple way of making sure you don't make any arithmetic mistakes. So the first step in the cycle then, which you're going to see in the next diagram, is this link here, which we already have, the enthalpy change of formation. To get from the elements to their ions, we've got to make them into atoms, we've got to atomize them, so it's going to be the lattice, the enthalpy of atomization. We've got to ionize the sodium, so that's going to be the first ionization energy of sodium, and then we've got to add an electron to the chlorine atom to make the chloride ions, so that's the enthalpy change, the first electron affinity. So you'll see these definitions, I'll deal with them as we come across them, but what I want you to do is keep in mind the general strategy, that what we're trying to do is work our way from here to here, and that will enable us to calculate this one. So here goes. Now I'm going to talk you through how to construct the Born Haber cycle that we will use to calculate the lattice enthalpy for sodium chloride. So this is an energy level diagram, so the lower something is on the page, the lower its energy, or the lower its enthalpy if you like. The higher it is, the higher its energy. So I've started off here just showing the enthalpy change of formation for sodium chloride. So the definition for the enthalpy change of formation, of course, is the enthalpy change that takes place when 1 mole of a substance or a compound is formed from its elements, everything in its standard state under standard conditions. And the enthalpy change of formation of sodium chloride is minus 411 kilojoules per mole. I'm not putting in the units because, as you'll see, the page is going to get rather cluttered. And what we've got to do is work our way up here and get from the elements in their standard states to the gaseous ions, and then the link between the gaseous ions and the solid, the ionic lattice, is the lattice enthalpy. So what I'm going to do is have lots of little energy levels, but every time I go from one to the other, all I'm doing is changing one, making one change. So the first thing we're going to do is we're going to get some sodium atoms. So I'm just going to write up there sodium atoms in the gas state, gaseous atoms, but I'm not going to do anything to the chlorine. So the chlorine is still Cl2 molecules, which of course in the standard state are gas. By making only one change between these energy levels, then every energy level reflects one of the definitions that we know. So going from here to here, we can ignore the chlorine because nothing's happening to it. That should be a Cl2, by the way. Let me I'm trying to keep things small so I don't run out of space. There you go. So we can basically forget about the chlorine because nothing's happening to it when we go from this level to this level. All that's happening is we're going from sodium in its standard state to gaseous sodium atoms. So the enthalpy change of atomization is the enthalpy change that takes place when 1 mole of gaseous atoms is formed from its elements in the standard state. And as you might expect, that's endothermic. I'll just write the enthalpy change. It's usually written like this, ATM, and I'll specify that it's for sodium because we're going to do the same for chlorine in a minute. And as you might expect, that's endothermic. It's plus 108 kilojoules per mole. So obviously to go from sodium solid, it's a piece of metal, to gaseous atoms, you've got to break it apart, you've got to put energy in. So that's the only change we've made there. And then we're going to do the same thing for the chlorine. Now, the chlorine is already a gas, but we don't actually have atoms. That's still Cl2 molecule. We've just got half of them. I know it doesn't seem logical because half of a Cl2 is clearly a Cl atom, but remember it's half of a mole, so it just means 3 times 10 to the 26, sorry, 3 times 10 to the 23 instead of 6 times 10 to the 23. So again, we're going to change only one thing, make one change as we go up the energy level diagram. So the sodium, you can effectively forget about that because nothing's happening to it, but we're going to change that half mole of chlorine molecules to a mole of chlorine atoms in the gas state. So to get from that level to that level, all we have done is atomize the chlorine. So I'll just write that there. It's delta H atomization for the chlorine, and the value for that is plus 122. 122 kilojoules per mole. Okay, so we've got the gaseous atoms, now we've got to make the gaseous ions. And again, going up to the next level, the only thing we're going to change, we're not going to do anything to the chlorine atoms, we're just going to form a sodium ion in the gas state, so that means removing 1 electron. And let's put in the energy level. You'll see why I've made it a bit longer in a moment. But the chlorine, we've not done anything to it, so just write there as a gaseous chlorine atom. So the reaction, or the enthalpy change corresponding going from this level to this level, is the first ionization energy of sodium. We've simply removed an electron from sodium. So as you remember from GCSE, it's not from GCSE, from AS, it's the enthalpy change that takes place when a mole of 1 plus ions is formed from a mole of the atoms, everything in the gaseous state, and each gaseous atom loses 1 electron. So that's endothermic, and that's going to be plus 496 kilojoules per mole. So we've got our sodium ion that we need to make sodium chloride. We now need a chloride ion, and we get that by adding this electron to the chlorine. Now, in this case, the reaction is exothermic, we're coming down. If you think about how you would show this at GCSE level, you would show the chlorine atom has 7 electrons in the outer shell, so it's in group 7, and if we add an electron, so typically that would come from sodium when you're showing the formation of the ionic bond, to make a negative ion, we would say that the ionic bond is forming, or the ion is forming, because having a filled outer shell, 8 electrons in the outer shell, is more stable than having 7. So if this is lower in energy than the atom, then we have to come down at this step. And indeed we do. We come down to about here. And if I write in what we've formed, we've got the sodium's not taking part, the sodium ion is not changing in that step. All we're doing is making a chloride ion, And the enthalpy change there, the definition that you need to know for that one, is it's called the first electron affinity of chlorine. So it's the first electron affinity for chlorine. Sorry, just chlorine, not chloride. I'll just put that in brackets. And that is minus 349. So it's intuitive. When you add an electron to a chlorine atom to fill its shell, it becomes more stable, lower in energy, so it's exothermic. And we put the first electron affinity because there will be examples where you have to put a second electron on. So you would have to, for example, to make the oxide ion, you'd have the first electron to give O minus and the second to give O2 minus. So you just got to watch out for those in the more complicated calculations. So now we're in a position to draw a line between the gaseous ions and the ionic solid, and this is the lattice enthalpy. Okay, so if you look in the textbooks, invariably they show these complicated strings of positive and negative numbers adding up and taking away, and to be quite honest, I wouldn't go there. I've never even tried to do it that way. There's a much easier way to go about this, and it is quite simply to imagine this as being a football field. Now, don't get me wrong, I'm not a fan of football, I've no interest in football, but football fields are very useful to help you understand Born Haber cycles, as I'm about to show you. So what I want you to do is imagine this whole diagram is this football field. So down at the bottom, this is the sodium chloride, and at the top you've got the very far end, you've got the sodium positive ion, the electron and the chlorine. Doesn't matter. What we're going to do is work out how long this side of the field is, and we know it's going to be the same length as this side of the field. So all we do is tot up the bits that we know from here. So going from here to here, I'm probably not going to get this to scale, but that is 411. Now I'm not even putting signs on it. You can think of it as 411 meters or 411 footsteps. You're walking up the side of a football field. So then you go another 108, and I say this is not to scale, so you go up another 108 meters, and then you go up 122 meters, and then finally you go up 496 meters. So what's the total length of that side of the field? Well, obviously it's going to be, you add all of these together, it's going to be 1137 meters. Okay, that's the length of that side of the football field. And then you get to that end, you decide to come back, but you're going to come down this side for a change, and you walk from that end, you just come down 349 meters. Again, don't need to use any negative signs or anything like that. And then you say, well, all we need to know is what's the length of this part. Okay, so how far have you got to walk to get back to this end? Well, it's going to be 788 meters. Okay, and that's the lattice enthalpy, but of course it's in kilojoules per mole. Now, of course, you have to apply a bit of common sense here, because this, we're coming down the energy level diagram, so the lattice enthalpy is going to be minus 788 kilojoules mole to the minus 1. So you could do 1137 take away 349 if you want, but I think a picture like that really makes it simple. And as I say, earlier on I think I said the value for the lattice enthalpy of sodium chloride was minus 771. You get different values in different books. This is one out of an AQA book, it doesn't matter. Just use the values that you're given. But that's how to go about lattice enthalpies. Now, just be aware that sometimes you have to do a double ionisation. If it was magnesium, you're going to have to take out a second electron, so you've got to include the second ionisation energy, and then if you're adding an electron on to, say, oxygen, first electron is the first electron affinity, the second electron is the second electron affinity. So I'm going to try and do all that, but it might get a little bit crowded, but hopefully now you can see what I'm doing. So So this second example, I've chosen to show you how we work out the lattice enthalpy for copper oxide using the Born Haber cycles. And I've chosen this one because you've got a doubly charged, positively charged positive ion and a double negative minus ion, so there are going to be more steps in the calculation. Okay, but if you stick to the method, remember whenever you put in a new energy level, there's only one change that you make, and that change corresponds to one of those definitions. And so I'm starting off here with the enthalpy change of formation of copper oxide. So there's copper oxide, CuO, in its standard state, 1 mole of it. And so to make that I need 1 mole of copper atoms, which copper comes in a solid state. And I need some oxygen. Oxygen comes as O2 in the gas state, but to get 1 mole of copper atoms I need half a mole of the O2s. Now if I now draw the next level, the change that I'm going to make is I'm going to make a mole of gaseous copper atoms. So I'm going from the element in its standard state to a mole of gaseous atoms. So that's going to be the atomization, enthalpy change of atomization of copper. And I'm not going to write in the symbols for what these are, otherwise it will get too crowded. But that is plus 339. So that's all I've done there is I've atomized the copper, and nothing's happened to the oxygen, so it's unchanged. It's just a mole of O2, or half a mole, excuse me, of O2 molecules. It's in the gas state, but it's still O2 molecules. Now you may think, what's the difference between half of an O2 in the gas state and an O atom in the gas state? But you've got to remember that these equations are for a mole, so that would be 1 mole, that would be half a mole. So if you think about, just draw a little picture of this. There's an O2 molecule. Imagine you've got a half a mole of those. Well, 1 mole will be 6 times 10 to the 23, so it would be 3 times 10 to the 23 of those. And you've got 1 mole of these will be 6 times 10 to the 23. So if I had a mole of these, I would get twice as many of these. So really, I've got 3 times 10 to the 23 of those. That's the same as 6 times 10 to the 23 oxygen atoms. I hope that's clear. Every O2 molecule you get would give 2 oxygen atoms. Let me show that. There's an O2 molecule, and that would give 2 oxygen atoms. So if I had a mole of this, a mole of O2 would be 6 times 10 to the 23 of them. Then I would actually get 12 times 10 to the 23, or 1.2 times 10 to the 22, of course. So I only need half as many of those, so I've got to have half of an O2. You don't need to worry about that. Right. Okay, let's continue and put in another energy level. So this time we're going to atomize the oxygen. So be guided by the definitions, then you don't need to worry about complicated things like that. The copper is not changing at all. It's not involved in this change. The only change is we're making a mole of O atoms in the gaseous state from the element in its standard state. So here's the equation for that. We're making a mole of O atoms in the gaseous state from the element in its standard state. Well, in the standard state, oxygen comes, it has to come as O2 gas, so we have to put a half there to balance it. We can't not put the half there and double this, because that would be for making 2 moles of oxygen atoms. So that's the enthalpy change of atomization of oxygen. And the value for that one, again it's endothermic, we have to put some energy in, and that is 249. So I'll write that there, plus 249. So now we've got the gaseous atoms, we've got to make the gaseous ions. So we'll start off with a copper, and we're going to remove, I think I'm going to run out of space if I go there. I'm going to remove 1 electron to give a copper 1 plus ion, and there's the electron I've removed from the copper, and nothing's happened to the oxygen, so that's just a mole of gaseous oxygen atoms. So that change corresponds to the first ionization energy of copper, which you remember from AS, and so that is plus 745. Plus 745 kilojoules per mole, first ionization energy of copper. But then we've got to take out a second electron from the copper. So the second ionization energy, again from AS, is going to give us a copper 2 plus from here to here, and then we've got another electron, so that's altogether we've got 2 electrons, and again nothing's happened to the oxygen atom. It is still 1 mole of gaseous oxygen atoms. So there's the energy level, and the change we have made corresponds to the second ionization energy of copper, and that is plus 1960 kilojoules per mole. And now we've made the, well, I better put the state symbol there. We've made the gaseous, the mole of gaseous Cu2 plus ions. We've got to start putting electrons onto the oxygen to make the O2 minus ion. Now, adding the first electron to oxygen, that gives us the O with a single minus. In fact, I'll write first of all the copper. We've not done anything to the copper, so the copper is Cu2 plus in the gas state. We've added 1 of the electrons onto the oxygen, so that gives us an oxygen with a minus in the gas state, and we've still got the 1 of the electrons left over. So that's the first electron affinity of oxygen, and you notice that it's exothermic, so we're increasing the stability, and that corresponds to minus 141, as we saw in the example with adding an electron to a chlorine atom. However, a slight difference now. We're going to put this second electron onto the oxygen, so that's the second electron affinity of oxygen. But this time we're going back up in energy, because you've got to try and add a negatively charged species, an electron, to a negatively charged ion. They're going to repel each other, so the closer you put them together, there's going to be repulsion, the energy is going to go up. So you actually have to put energy in to add this second electron to oxygen. So what you make then, if I just make that one a bit shorter, what you make, we've not changed the Cu2 plus in this change, and we've finished up with an O with a 2 minus gas, and we've got up, and the enthalpy change, the second electron affinity of oxygen, is plus 790. Now this is nowhere near to scale, is it? I can see that. Plus 790, but if I went to scale it would be off the top of the page, or off the top of the screen from where you are. Now we're ready to complete the Born Haber cycle. We've got the gaseous ions, and when they come together to form the ionic solid, that would be the lattice enthalpy. Now again, what I'm going to suggest that you do is treat this as a football field, and we've got a little extension at the top, that's all, but it's quite simple. The method still applies, and I'm just going to draw a rectangle here. From where I'm sitting, this is a rectangle, but I appreciate on the screen it's probably sort of distorted because of the camera angle. But let's just work our way. We're going to walk around this football field. We're starting down at the bottom here, so we walk along this side 155 metres. We walk, have a chat with somebody. We walk another 339 metres. Have a cup of tea. Then we go up 249 metres. Then we see somebody else we know. We go 749 metres. Sorry, 745 metres. And then finally we go right up to the top here, and it's another 1960 metres. Again, not to scale. Point is, don't worry about signs or anything like this. That's the total length that we've walked in that direction. Now, before we get to this corner, we I'll do it like this. See how when we're at this end of the field, we've done this, we've got to here, we've come back again, we've come back 141, so I'll just put minus 141, and that brings us to here, and then we've gone off again 790. So if I join it up, it's a bit of it's a rectangle, but with a bit of a funny ending there. I can still sort of extend it and treat it as one rectangle. So up to here, it's 155, 339, 249, 745 and 1960. That gets us to here. We come back on ourselves 141 metres, and then we go forwards again 790. So the difference between those two, if you do 790 take away 141, we've advanced 649 metres. So this little bit here is 649. Okay, so you're standing at this point here, and you come back 141 and then forward 790. It's as though you've just gone forward 649. So all we have to do is add up all of these values. So 155, 339, 249, 745, 1960, and then we just add on to that 649, and that comes to 4097. And I'm writing it on this side because this side of the rectangle or the football field is going to be equal length to that side. Or what you could do is you could just add all of these together and then subtract 141 and then add 790. It doesn't matter. I think if you just draw it like that as a shape, it's much easier than doing these strings of numbers. And so as you see, that corresponds to the lattice enthalpy, but with the sign changed. So the lattice enthalpy for CuO, lattice enthalpy for copper oxide equals minus 4097 kilojoules mole to the minus 1. It's as easy as that. Okay, no need for arithmetic errors. So what I'm going to do next is explain to you how we interpret lattice enthalpy values calculated using the Born Haber cycle and compare them with theoretical values that we can obtain, and that gives us an insight into whether a compound is indeed purely ionic or whether it has some covalent character. Okay, so we've just seen how you can obtain lattice enthalpy values by using a Born Haber cycle, but there is another way to obtain them, and this is based on a calculation. So this is a theoretical value, and it's based on the assumption that the only form of bonding in the compound is ionic bonding. Whereas the Born Haber cycle, because we're inputting experimental data, this is actually the observed value. Now sometimes there's very good agreement between the two approaches, and sometimes the agreement is not so good, and I'm just going to show you some examples of that before we look at the reasons for that. Here we're looking at two compounds, lithium fluoride and magnesium iodide. First of all, look at the lithium fluoride. The experimental value obtained by putting the experimental values into the Born Haber cycle gives the lattice enthalpy as minus 1031 kilojoules per mole. If you calculate the lattice enthalpy, and that's based with the assumption that there is only ionic bonding holding the ions together, you get very good agreement. So really we can say that ionic bonding largely accounts, or almost entirely accounts, for the strength of the bonding in the lattice of lithium fluoride. But compare that with a magnesium iodide. If you measure the lattice enthalpy using the Born Haber cycle approach, you get minus 2327 kilojoules per mole. If you do a calculation in which you assume that the only form of bonding is ionic bonding, you get only minus 1944 kilojoules per mole. So remember, this being more negative than this one means that more energy is released when the ions come together from the gas state. That means they're held together more strongly the more negative this number. So what we're saying is that ionic bonding on its own cannot account for the strength of the bonding in the lattice of magnesium iodide. You can look at it in the other direction. If you wanted to take some solid magnesium iodide, the ionic lattice, and break it apart so you're producing individual ions in the gas state, based on this calculation you would only need to put in 1944 kilojoules per mole, but in practice you would need to put in 2327 kilojoules per mole. You'd have to put in more energy, so the ions are being held together more strongly than can be accounted for on the basis of ionic bonding in magnesium iodide, whereas in lithium fluoride, it fits the model very well. It's only really ionic bonding is all you need to account for this. So in this case, the difference between these two is the contribution of covalent bonding. So although we think of magnesium iodide as being an ionic substance, we say it has some covalent bonding or some covalent character that's contributing to its strength. Okay, here I have made a pretty lousy attempt to draw a representation of some positive and negative ions in an ionic lattice. And all I want to do is give you an idea of how people go about calculating the lattice enthalpy of a compound, assuming that the bonding is only ionic. So what they do is they look at the attractive forces between the oppositely charged ions. So obviously negative ions are attracted towards positive ions, and these forces of attraction can be calculated using an equation, but we don't need to be concerned about the equations. But the point is that the bigger the charge is, the more powerful these attractive forces. So if you had a 1 plus and a 1 minus ion, the attraction between them wouldn't be as powerful as if you had a 2 plus and a 2 minus ion. So the more highly charged the ion, the more powerful the ionic bond. So you can input that into the equation, and that's going to give you an idea of the strength of the ionic lattice, so the lattice enthalpy. But you've also got to consider the forces of repulsion, because like charges repel. So you've also got this one's going to be moving away from this one, and similarly this one's going to be moving away from this one. So all of this is put into the equation based on a knowledge of the arrangement of the ions in the lattice. But you also need to know the distances between the ions. So you need to know the distance from the centre of this ion to the centre of this ion, and this one and this one. So there's quite a lot of trigonometry in there. But based on that, it's possible to work out the lattice enthalpy, the strength of the ionic bonding in an ionic compound, but it considers the bonding as being only ionic. Now that works reasonably well, as we've seen for the lithium fluoride, but it didn't work quite so well for the magnesium iodide, and I'm going to explain that to you now. So here is an iodide ion. I've drawn it large because it is a large ion, lots of electrons, and I want you to think of that as being like a wobbly jelly. It's easily deformed. So if we put alongside that the magnesium ion, now the magnesium ion, it's relatively small and it's got a 2+ charge. So we say it's got a high charge density, a lot of charge for its size, and because this is a large ion, the electron cloud around the nucleus is easily distorted. These electrons in the outer shells, they're a long way from the nucleus, so they're not held quite so tightly, and so they can be distorted by the magnesium. So what's going to happen is, it's not just going to sit there and be that shape, it's going to, its cloud of electrons is going to sort of get drawn and distorted over the magnesium, then eventually you will get a little bit of overlap between the electron shells, if you like. So we've got the magnesium ion there, and we've got the iodide ion here, but in some regions there will be overlap, so there'll be a component of ionic bond, of covalent bonding. Covalent bonding is of course shared pairs of electrons. It occurs when orbitals overlap to give molecular orbitals. It's still primarily ionic bonding, but there is a component of covalent bonding in here. Now of course I've drawn this just for one iodide ion. In practice there would be 2 iodide ions for each magnesium, so you'd have the same thing repeated over here. But the point is that when you get a large ion, a large negative ion, next to a highly charged small ion that's positive, you will get this distortion and you'll get a contribution of covalent bonding. So the bonding in magnesium iodide, it's primarily ionic, but there is a component that is covalent, which is why the lattice enthalpy in practice is more negative than that calculated based purely on ionic bonding. So here then I've just summarised the circumstances under which this covalent character is seen in ionic compounds. When the positive ion has a high charge density, so we mean a high charge and a small size. So good examples would be the magnesium ion we've just seen, but also the aluminium 3+ ion. It's got a high charge, relatively small volume, so that's very good at distorting negative ions. And for the negative ion to be distorted, the larger its size, the bigger its volume, the more easily it's distorted. Think of it like a jelly, but the more negative its charge, the bigger the negative charge. So the sulfide ion, for example, S2-, that would be easily distorted. Okay, just to finish off, I'd like to show you one or two interesting manifestations of this phenomenon, the role of covalent bonding in ionic compounds. Here we have the aluminium halides. You are taught at GCSE that a metal plus a non-metal always gives ionic bonding, and that's the case for aluminium fluoride, but the other halides, they're all covalent. They're considered to be covalently bonded. And of course that's because the aluminium ion, high charge, small volume or small surface area, highly polarizing, so it's very good at distorting negative ions. And it's only the fluoride ion that's small enough to resist that. Its electrons are relatively close to the nucleus, so held rather tightly, so unable to be drawn over to the aluminium 3+ ion. But in the case of the others, the extent of that distortion of the electron cloud is so much that we consider the bonding to be covalent in those substances. Okay, this final example, and I promise it is the last example, I'd like to clear up something that causes misunderstanding in students when it comes to the covalent character of ionic compounds. And what I want to show you is that even when you have a contribution of covalent bonding in an ionic compound, it doesn't necessarily make the overall bonding stronger than in an ionic compound that doesn't have a covalent character or has less covalent character. So the examples I've chosen here are magnesium oxide and magnesium sulfide. So in both cases we've got the magnesium ion, Mg2+, Mg2+, but the negative ion is different. Obviously we've got the oxide ion here, the O2-, and the sulfide ion here, which is larger. I'm going to exaggerate this, but the sulfide ion is larger than the oxide ion. You've got an extra shell of electrons. Now, because the sulfide ion is that much larger, it's more easily distorted by the positive ion, by the magnesium ion. So in magnesium sulfide you're going to have more covalent character, more overlapping of the electron shells. Now I'm not saying you don't get any overlapping in magnesium oxide, but it's going to be less simply because the negative ion is not as large as the sulfide ion. So you might think that by having some covalent character to add on to the ionic bonding, the bonding in magnesium sulfide is stronger than magnesium oxide, but it's not, and that's because by having a larger negative ion, the distance between the ions is going to be larger too. So the underlying electrostatic force of attraction between the magnesium and the sulfide ion is weaker because it's acting over a longer distance. In the case of magnesium oxide, the two ions can get much closer together, so the underlying ionic bonding is stronger. So this is where you've got to offset one factor against another. You've got to think about the underlying strength of the ionic bonding, what's affecting that, and then the contribution of any covalent character. So in the exams they can give you all kinds of combinations of ionic compounds to consider, and you mustn't just focus in on one factor, one parameter. You've got to look at the difference in the values and then try to rationalise that by applying all these different phenomena. So if it's just down to ionic bonding, then that's increased in strength by having big charges, large positive, large negative charge, and small ions. The ionic bonding is weaker by having a larger ion, and yes, you do get some covalent character here, but that's not enough to offset the weakening of the ionic bonding due to the increased distance between the ions. So that's the end of this video. I hope you found it helpful, and I'm going to produce a video next on the use of Born Haber cycles for looking at enthalpy changes in solution. So thank you very much for watching, and do please subscribe to the channel, and that way you'll get updates with each new video that comes out. Okay, thanks again, bye.